Hi, everybody, and welcome to live stream broadcast on my YouTube channel. And this is Theoretical Physics with Mark Weitzman. I'm doing a live stream, the third one on group theory with Schensted's book. And so today we'll do the group theory. Sorry about that. Group theory. Let me just get group theory in physics. Live stream 3, and we'll continue with lecture 3 of Schensted. And the main thing we'll do today is we'll cover some major theorems. Concerning representations of finite groups. And some of this these theorems will carry over to some, usually compact, infinite groups. And I don't know what happened there. Maybe it takes a while. Okay. And so some of these we'll use later in the course when we get to infinite groups, but right now we're just doing finite groups. And today I'm going to follow my notes, my LaTeX notes on pages 18 to 21, which are available on the Piazza site, and also pages 31 to 35 in Schensted's book. So we have major theorems. And what I want to do is I just want to go to my notes and see, I knew I hit something. Sorry about that. So I want to go to my notes. Let's see if they come up. Okay, so these are my LaTeX notes. They're on my Piazza site, and I've copied liberally from her. Hopefully I'll get a 2-to-1 compression when all is said and done. But so I want to cover some of the major theorems. And these theorems were developed early in the 20th century by Frobenius and Schur. And the first three sort of work up to proving the very valuable fourth theorem. And the proofs are given in just about every textbook on finite group theory. They're not difficult proofs. And they're given in Schensted's book in Addendum C. But the proofs aren't that important. I mean, you should read them, but it's the results that are really important for physics. So let me start just by reading my notes. And So any representation of the group G by matrices of non-vanishing determinant, meaning non-singular matrices, can be transformed into a representation by unitary matrices by a similarity transformation. So let's see what this means. This simply means that if I have well, doing the major theorems right now, major theorem 1, unitary reps. First of all, let me clarify that some authors are a little bit lazy, or they don't state, like I won't name them, but some of them say that all reps are unitary. That's not true. There are non-unitary reps for all the finite groups, but they're equivalent to unitary reps. And if two reps are equivalent, basically we can work with either one. So we can always work with unitary reps for the most part. There are some exceptions. We'll get into that when we discuss vibrations and small oscillations and non-unitary reps. Now, so we have these unitary reps. So if we have like a representation gamma, what this means is, and let's say gamma is non-unitary. What it means is we can find a matrix S, so that S gamma S inverse, and this is like for all elements G and G. Same thing here. We'll call this gamma prime, and gamma prime is unitary. So this is just a similarity transformation. S is non-singular. And to see how this works is very trivial. But let's say we have three elements like G1, G2 equal G3. So a representation, this implies that gamma of G1, gamma of G2 equals gamma of G3. Now, we can multiply this by S. Let's go S, gamma of G1, S inverse, S. Notice S inverse is I, so that's not doing anything. Gamma of G2, and on the right side we get S, gamma of G3, S inverse. So this is just gamma prime G1, gamma prime G2 equals gamma prime G3. So if gamma is a representation, then gamma prime is a representation. So any similarity transformation will have this property. And what the theorem says is there exists a similarity transformation such that gamma prime is unitary. That's very, very helpful. Okay, let's go to the next theorem. Theorem 2 is called Schur's lemma, and it says a matrix which commutes with all the matrices of an irreducible representation is equal to a multiple of the identity matrix. So this theorem is sort of a lemma. It's called Schur's lemma, and I won't say much about it. This and the next theorem enable us to prove theorem 4, which is the important one. So let me read theorem 3. Consider two irreducible representations of the group G. Group G is a finite group, elements A1 to AN. These are the representation matrices of dimension lambda 1, call it gamma 1, then gamma 2 of dimension lambda 2. If there exists a matrix M with lambda 2 rows and lambda 1 columns such that, now, M is lambda 2 by lambda 1, which is what it needs to be because you're going to multiply by a matrix with lambda 1 by lambda 1. So the final is going to be lambda 2 times lambda 1. Gamma 2 is lambda 2 times lambda 2, and m is lambda 2 times lambda 1, so that works out. So either way, both of these on both sides of the equation, we're going to end up with a final matrix, which is lambda 2 by lambda 1. Okay, now it's saying that if lambda 1 is unequal to lambda 2, in other words, these aren't, these representations are different, the matrix M is a null matrix. All elements are 0. So we can't have this happening if the representations are of different size. On the other hand, if they're the same size, if lambda 1 equals lambda 2, then either, this is a typo here, that should be then, I'll have to fix that, then M is either a null matrix or a matrix with non-vanishing determinants. And in the latter case, M has an inverse, and the representations are equivalent because we have M gamma 1 equal gamma 2M, multiply this by M inverse, and it's the same, or multiply this by M inverse, and it's the same similarity transformation we had earlier. So this is another technical lemma that's needed to prove the all-important. So let me go back to the iPad here for a second. So theorems 2 and 3 are technical lemmas, and these aren't hard to prove, needed to prove the all-important theorem 4. That's what we'll do right now. Theorem 4. I'll go back to my notes. Theorem 4. If gamma ig and gamma kg are two irreducible unitary representations. So when I is unequal k, this is how we're labeling the irreducible unitary representations. When I is unequal to k, these are inequivalent irreducible representations. But when I is equal to k, we don't just want equivalent, we want identical. And this is a point I never really understood. And I was reading Georgie's book on Lie algebras recently, and he emphasized the point. We can always choose, if two representations are equivalent, we can always choose to work with the same representation. So this has got to be identical here, not merely equivalent when I equal k. Then we have this formula. It looks like a very long and complicated formula, but after a while in group theory, you'll get used to these formulas. First of all, there's a summation over the group elements. So notice that J is the summation index, and we're putting every group element in, we're putting, hold on, let me just respond to the chat. So we're putting every group element, we're going to sum over every group element. Now we're taking one representation. The indices are fixed. Mu nu can be any indices on that. We're taking the complex conjugate. And there's a footnote here where what you do when you're not working with unitary representations. But for now, let's just think we're working with unitary representations. And then we have the other representation, the same group element, different indices. This whole sum is going to equal n. N is the order of the group, how many elements are in the group, A1, A2, up to AN. Lambda I is the dimension of the gamma I representation. Now you might say, why is it gamma I? Why not gamma k? Well, there's a delta ik here, so it only matters, you know, if lambda I and lambda k differ, then it's just 0. If they have different dimensions, then it's just 0. If they have the same dimension and they're equal, then this will be equal to 1. And I should point out, you can have irreducible representations of the same dimension. You can have a three-dimensional representation and another three-dimensional representation, and they don't have to be equivalent. So it's not just that I equal k. We label the irreducible representations. The lambdas are the dimensions. They could be the same for several inequivalent irreducible representations. Okay, and then it depends on delta, a delta function of the indices, mu and mu prime, and nu and nu prime. So so here, when you analyze the meaning of this theorem and see how it's so useful, we could think of gamma I, aj, mu, nu. We fix I, we fix mu and nu, and we just go over the group elements. So we get an n-component vector because there are n group elements. And this equation is basically saying that these n-component vectors are orthogonal if either the representations are different or the indices that we're using to place in the matrix are different. So if we look at a specific representation, gamma ig, we would see that there are lambda I such vectors because the dimension is lambda I, so mu can go from 1 to lambda I, and nu can go from 1 to lambda I. It's a lambda I by lambda I matrix. And so we have lambda I squared such vectors for a given representation, gamma ig. Now, by linear algebra, we know that there can be at most n mutually orthogonal n-component vectors. You know, if you have like 4 component vectors, you can only have 4 that are orthogonal. 5 won't do it. They won't be independent. So we obtain the following inequality. Lambda 1 squared plus lambda 2 squared plus dot 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 lambda I squared over all the irreducible representations is less than or equal to n. So this already tells us something. It tells us that there are only a finite number of irreducible representation. We usually label we have R irreducible representations. These are distinct, inequivalent, irreducible representations of a group of finite order. Now it turns out, we'll prove later, but you need more machinery to prove it, that in fact, this identity, I'm going to go back to my iPad here. This identity that, theorem 4, it implies the following identity. Lambda 1 squared plus lambda 2 squared plus dot 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 lambda r squared is equal to n. This is an amazing relationship, and I want to show what it means. So let's think about this. If we have an abelian group, all representations, I think we established this earlier in the course, are one-dimensional. So this implies that there are n irreducible, inequivalent representations for an abelian group of order n, has n elements. And this is, for those of you who have studied Fourier analysis, there we're dealing with an abelian group, a cyclic group. And you might remember that there's all these representations. You know, we have like, I don't remember exactly how it goes offhand, e to the I, omega, K, and what we'll find is like K will be equal to like 1, comma, 2, comma, dot, 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 n. In other words, there'll be n representations like a typical Fourier analysis. It just goes from the modulo of the integers. So that's a simple consequence for abelian groups. Let's take the group, Schensted calls it GB. This is isomorphic to S3. This, the permutation group on 3 objects, isomorphic to the dihedral group on 3 objects. Remember, we had a triangle, and there were 6 symmetries. We could rotate by 120 degrees. Could rotate that there. We could rotate by minus 120 degrees. So those are 2 rotations. So here's the center of the triangle. And then we could reflect around these 3 lines. So we have altogether the identity, the group, GB is equal to the set consisting of the identity, C bar, this is the notation she uses, sigma, I think if these are the vertices like A, B, C, we'll have like sigma A, sigma B, sigma C. So if we wanted to understand this representation, we're going to have lambda 1 squared plus dot, 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 lambda r squared is equal to 6. Now, we know that for the permutation group, permutation group always has lambda 1 equal 1 and lambda 2 equal 1. There's always, every group has the trivial representation. The trivial representation is gamma of G equals the number 1 for all G in the group. So that's a trivial representation. The permutation group, Sn, permutation on n objects, has a another 1D rep. It's called an associate of the trivial representation, where gamma G is equal to 1 if G is an even permutation. And we'll discuss permutations in much more detail later. And gamma G is equal to minus 1 if G is odd. So that's another one-dimensional representation. So lambda 1 is 1, so we end up getting 1 plus 1 plus dot, 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 lambda r squared equals 6. So what are the possibilities? Well, we could have 4 more one-dimensional representations. So this is case A. But that won't work because this group is non-abelian, and one-dimensional reps are always abelian. So we need, okay, so this is no good. We need at least 1 rep with lambda greater than 1. Another way to think about it is that we'll prove later another theorem. That the number of irreducible reps is equal to the number of cycles in the group. I'm sorry, number of classes in the group. We haven't talked about classes yet. We will next time. Okay, and S3 has 3 classes. Basically, classes are like sets of elements which are similar. They have different names, but they're really similar. And you can see in GB that the 2 rotations are sort of similar in what they do. That's one class. The identity is always in a class by itself. And the 3 reflections, they're also very similar, so that's another class. So this is one class, this is a class, and this is a class. So we have 3 classes. That means there are 3 irreducible reps. We already have 2 of them. So the only possibility, case B, is only possibility is 1 squared plus 1 squared plus 2 squared equals 6. And that works out. And if I'll go back to my notes, last week I showed you a bunch of representations. I showed you this big table here. These are all representations of the group. These are the group elements, and these are the this is like 6 different representations, and these are the representation matrices. As I said, the first line is the trivial representation. The second line is like the associate representation. Both of these are one-dimensional. The third line here is a two-dimensional representation. And I will show in a second that this is in fact an irreducible representation. So these are our 3 irreducible representations. Gamma 4, on the other hand, is actually a combination of gamma 1 and gamma 3, as you can see. If you sort of take out the block there, it's 1, 1, 1, 1, 1, 1, and then the rest of it is the same as what's above here, the 2 by 2 block. So gamma 4 is reducible in terms of gamma 1 and gamma 3. Gamma 5 is the defining representation, and now we know that it too is reducible. Gamma 6 is what we call the regular representation. We'll talk more about these, and it also is reducible. Now let me get back to some additional theorems. So this orthogonality relationship is like very fundamental to finite group theory representations. And we can, from this, we can go on to characters. So I want to talk right now about characters, because characters are very important. The definition of a character is the trace of a, if we have a representation, the traces we denote it as chi aj. We think of the matrix gamma aj, and we sum over k, kk, usual definition of the trace. And this is called the character of aj in the representation gamma g. Now the great thing about traces, as you know, is that they're invariant under similarity transformation. And we can show this. I'll show this. It's so trivial, but so if we have like S gamma S inverse, and we want to take the trace of that, it's well known that the trace is cyclical. You can show this with the indices. I won't do it for you. You should put in indices and prove this, but this is going to equal to S inverse S gamma. It's a trace of that, which is equal to the trace of gamma. So characters don't matter which, as long as you're in an equivalent representation, they don't care which one you're in. Let me get back to my notes here. And so using the orthogonality relationship if we set mu equal nu and mu prime equal nu prime and sum respectively, so go into this equation and do exactly what I said. Set these two the same. That will give you the character complex of the character there in that representation, and then in the other representation. So we're going to get this very important formula. The sum of the group elements of the character of AJ, the complex conjugate, times the character in the other representation of AJ is n del ik. So if we're working in different representations, then the character vectors, which can also be thought of as an n component vector, are orthogonal. And we can get an important criterion for reducibility and irreducibility as follows. Let me just go back a second to my iPad. We can always, when a representation is reducible, a reducible rep, actually any rep for that matter, can always be written as gamma of the group G is equal to the sum over I, AI. AI are integers of gamma I, G. So remember, we had this big matrix of all the elements, and they're all can be put in like block form. Some are bigger than others, and so on like that. So we have these block forms. Sometimes these blocks occur more than once. They're the same. Sometimes they're different. Sometimes these are integers. So what we're saying is that if a representation is reducible, we can write it in terms of irreducible reps. These are the irreducible ones. And how we combine them, what these integers are, we don't know. But if you now take the trace of this formula, you're going to get chi of aj, let's say for any given element, is equal to the sum from I equal 1 to r over all the irreducible representations of ai chi I aj. So that's a nice relationship. This is for all the group elements. And now, if we take the absolute value square of both sides and use the orthogonality relationship, let me go back. So we're going to square this. There's r terms. We're going to get all kinds of terms, but all of the cross terms vanish because when I is different, it's 0. So we're going to end up with just this equation. The sum of over the group elements of the absolute value of the characters for each element squared is equal to n times the sum from I equal 1 to r of ai squared. Now, the argument goes as follows. If gamma I is irreducible, gamma G, that just means that one of the AIs is equal to 1 and the others are 0. And then we get that if we have an irreducible representation, the sum of the characters over the group elements of that representation is equal to n. And if gamma G is reducible, then either one of the AIs is greater than or equal to 2, meaning it has one representation twice, or more than one AI is equal to 1. Either way, we get that this sum is greater than n. So let's go back to that table we had and see. I said gamma 3 is irreducible. Let's look at the characters. Let's look at the characters for gamma 3. The identity element has a character of 2. 2 squared is 4. The rotation has a trace of -1, so its squared is 1. We add it to 4, we get 5. The counter rotation is the same thing. We get 6. And notice that these three elements all have traces of 0. Half minus 1/2. So now we have the sum of the traces is 6, which is n. So This in fact shows that gamma 3 is irreducible. Let's apply it to gamma 4. Well, gamma 4, we have 1 plus 1 plus 1 is 3. 3 squared is 9. So that's already greater than n, which is 6. So we know gamma 4 is reducible. If we were to take the other traces, this is minus 1, 1, this is 0, this is 0, this is 1, so we get 9 and 1 is 10. This is 0. I'm sorry. 2 minus 1 is 1. Okay, this is 1. No, this is 0. This is a trace of 0. This is a trace of 0. This gives me 10. This is a trace of 1, which gives me 11. And this is a trace of 1, which gives me 12. So you're always going to get a multiple of the number of elements in the group. So it's 12, and therefore it's reducible. And you can do it with these two, and you'll see that these are all reducible. So that's a nice way to see if a representation is irreducible or reducible. And these rules, these orthogonality theorems for characters, they sort of let you, it's easy to get the characters for small groups. Now, there's another formula we can get. It's the same thing you do in Fourier analysis. To get the coefficients AI, we do the usual procedure of inversion. For orthogonal expansions, we multiply both sides of 47, which is this. We multiply it by chi k aj star, so this is the irreducible representation, chi k, and then sum over j, and then we use this orthogonality relation to get rid of most of them, and we get this extremely important formula. The number of times a given representation occurs, like chi here corresponds to gamma, and chi k corresponds to gamma k. So this is an irreducible representation. This we don't know, it's some representation. And if we want to know how many times the irreducible, the k representation appears in gamma, we compute this formula. 1 over n, the number of group elements. We sum over the group elements, take the complex conjugate, and multiply it by the character. So let's do an example here for, let me do it on the iPad. So we have this character analysis formula. Again, we have gamma. I'm just going to copy what I wrote here. Gamma of G is the sum over I of AI gamma IG. So these are the irreducible reps over here. These are integers. And now we can get those integers by saying that AK is equal to 1 over n, the sum over j, chi k aj star chi aj. So let's apply this to the gamma 6. Well, first of all, n is 6. And let's look at the gamma 6 representation. If you'll notice, the identity has a trace of 6. It's 1s all along the diagonal. So the trace of the identity element is 6. But if you look carefully at all the other matrices, and this will always be true in the regular representation, all the diagonal elements will be 0. So all of the traces of all of the other elements are 0. So if we want to know how often does A1, the trivial representation, occur in gamma 6, it's 1 over 6. We know the regular representation only applies for the identity element, so we're just going to get chi k of E star times chi of E, which we already established was 6. Okay, so this is equal to, the 6's cancel, it's just chi k of E star. And this is 1 because the dimension of chi 1, we're doing A1. So this is 1, A1. The trivial rep is one-dimensional, and the identity element is represented by 1, so this is just equal to 1. So the trivial representation occurs once. Now for the non-trivial representation, it's the same thing, because on the identity element they have the same character, because the identity element is an even permutation. So we're going to get the same thing. And then our third irreducible representation is A3. So here we're going to get 1 over 6 chi 3E star times 6. Now we have to look back. What is chi 3E star? If you remember, it's a two-dimensional representation, and the identity element is represented by this, so its trace is 2. So this is equal to 2. So this tells us that gamma of 6 is equal to gamma of 1 plus gamma of 2 plus gamma of 3 will occur twice. So this is like 2 gamma of 3. So this is like gamma 1 plus gamma 2 plus gamma 3 plus gamma 3. And if you were to break it down, remember the regular representation is 6-dimensional. This means we can put it in block form as follows. We have 2 one-dimensional reps, but they're not equivalent. These are 2 different ones. And then we have 2 two-dimensional reps. These are equivalent because there's only 1 two-dimensional rep. So that's how this is like 2 by 2, 2 by 2, 1 by 1, and 1 by 1. So that's how the regular rep decomposes. And it's a theorem we'll prove later that the number of times each irreducible representation occurs in the regular rep is equal to its dimension. So the trivial dimension is of dimension 1, it occurs once. The associate rep is of dimension 1, it occurs once. The two-dimensional irreducible representation is of dimension 2, so it occurs twice. And I didn't show that. So this is just what I drew here. Sorry, I didn't show it. These were the calculations. A1 is 1, A2 is 2, A3 is 2. And that's how it works out. In my notes, I do the calculation here too. A1 is 1, A2 is 1, A3 is 1. So that's as far as I want to go today. And next time we'll go into the applications of quantum mechanics. So we haven't really done any physics in this course, just some group theory and representations. And next time we'll talk about like selection rules. There's a lot of physics that you can get out from in quantum mechanics. The symmetry group of the Hamiltonian, perturbation theory, how it all works out. Things that you might not be that comfortable when you take it in a quantum mechanics course, but now you'll see how it arises, like this kind of splitting where you start with one group and then the level splits, and then the level splits again. In this particular example, you'll see why this one splits again, but this one doesn't. And then we'll finish with a slight discussion of continuous groups. And then I also want to cover, there's a lot in that we didn't cover about classes and invariant subgroups and projection operators are very important, and direct products of matrices and direct products of groups. So thank you all for watching, and I'll see you next time. In case you, I also posted a video, not a live stream, but a video on vibrations and small oscillations, which is a topic that I'll cover after we get through Schensted. I'm sort of going a little out of order, but the first video didn't require any group theory, so you might want to look at it. It's on the playlist and also on my Piazza site. Thank you very much. I'll see you later.